All right, welcome everyone to our session of Cloud Native Security. My name is Martin. I'm an application security engineer at VMware Carbon Black, working on security products. And I yield the floor to my colleague, Anton.
And I'm Anton. I am a senior software engineer, also at Carbon Black, where I'm working on a product for containers and Kubernetes security. So today we're going to talk about cloud native security and how to implement this through the whole lifecycle from development to runtime. But first of all, let's talk about what is cloud native. Cloud native is a set of practices to run, build, and operate applications in public, private, and hybrid clouds. So different companies might approach this in different ways, but when we are talking about cloud native, a few patterns come into mind. That is running multiple microservices that run in containers, working in DevSecOps teams, and using GitOps workflow to manage the declarative infrastructure as code. So let's say a few words about these patterns. What is containers? This is a lightweight way to build and package and run software, where the software itself, alongside everything that it needs, is packaged inside a container that can be distributed and run anywhere where you can run containers. The big difference when comparing to VMs, for example, is that with containers, you have everything packaged inside the container, and the only thing that you need is a host, a container engine, and a kernel, a host kernel, which the container is going to reuse. So a container doesn't need its own kernel. DevSecOps, this is a methodology where development, operations, and security teams are not different teams, but are actually one team working together. So it could be one team with multiple people with different backgrounds and different responsibilities, or it could be one team of people who are all working on all these three things: development, operations, and security. And for the last two things, infrastructure as code is a process where you are not managing infrastructure from the cloud console or by hand. Instead, you have your infrastructure defined as code in text files, and you have a tool which you use to apply these files to your environment. And this tool is responsible for creating the infrastructure and making sure the desired state, the actual state, is equal to the desired state, which is in these files. And GitOps is the process of using Git as the source of truth for our operations. So whenever you want to make a change, whether it would be in the application code or in the infrastructure as code, you make a change, you open a pull request. Once that is merged, it triggers a CI pipeline which applies these changes. So Git is not only the source of truth for the state of our infrastructure, but it's also the main platform of collaboration between the DevSecOps teams.
All right, so cloud native computing. Now, what security challenges we face? First of all, the very concept of going cloud native means that we actually break a big monolithic application into different services. So naturally, one of the first things that comes to mind is securing those numerous services. Instead of before having one application, now we have many, many different services. So naturally, this is a little trickier to secure. So these different services, they have different requirements. They also have different patterns of communication, what service talks to what other service, what is allowed, what is not, what are all the services that are actually available in our environment. How do we tell them apart? Also, secrets management. Before, with the monolithic application, everything was somehow more straightforward. It's just the application. It has access to whatever secrets it needs. However, once we go into services, it means that, for example, we have a service talking to a database, another service talking to only internal services, and also there will be some services that will contact external providers, cloud providers, and so on. And all this happens inside some infrastructure that's also more complicated. It's harder to manage, at least initially. As Anton mentioned, what we should do is have GitOps. So infrastructure is not only written in configuration files as code, but also we have a single source of truth. What is the desired state of the infrastructure? Who makes changes? What changes are being made? It helps a lot to have a consistent state, the desired state of our infrastructure, so that we don't end up with the state drift. For example, people logging into the infrastructure, manually doing some dynamic changes that eventually could lead to problems. So the cloud native continuous lifecycle, of course, going left to right from development to building our artifacts, preparing and deploying artifacts, publishing them in registry, and finally going into the actual runtime where we can make use of this. So this can actually be broken down into 4 phases: develop, distribute, deploy, and runtime. This whole topic actually is a very big topic. It's both broad, but it gets very deep in different areas. So today we'll try to cover the high-level overview with some more specific examples on different security controls and security practices that we can implement and we can do within the continuous lifecycle. Truth be told, these phases are not exactly strictly cut and distinguished one from another, because there are some controls that might happen in one of the phases, but they might also be reused or they're somehow relevant in other phases as well. And we will have such examples. So let's start with the develop phase. This is probably the thing that most naturally comes from the monolithic way of thinking and of working. So development, even before actually writing code, we have some requirements. Ideally, we have also the security requirements for our application. Once we have the architecture, and ideally before starting writing code, we should also do threat modeling. So threat modeling actually helps us look at our architecture from a security point of view. Are there things that are probably not as good as they should be? Or are there things that are maybe okay, but we need to pay special attention to those, like managing some sensitive data or communicating with external services that might or might not be as trusted. Also have the very traditional code review, not only for security, but for product quality in general. So the next step is the distribute phase. We are showing this picture again. It will come up several times in our talk today, just to keep us all on the same page, what we mean by different phases and where the particular control happens. So the distribute phase, once code is being pushed to a repository, from then on, we have some continuous processes like continuous integration, continuous delivery. The code is taken, artifacts are built, and then you can do something with these artifacts. So the first thing I want to focus and deep dive a bit into is container image scanning. So far we mentioned containers, but what is a container image? So the container image is the static information about the container, and the actual running container starts from this container image. But the image itself is the static data. So in order for us to present this in a more illustrative way, there is a simple example with an application. We'll be adding a scanning stage for that application and see how this application evolves naturally. I'll be sharing the development perspective here, but also the application security perspective for this whole process. So let's take one application. In this case, it's a very trivial application. This one is written in Go, but this is just for illustration. It can be, of course, any application, any service, any language. So this one is a trivial example. Of course, we might have, and we want to have more meaningful products and services that are warranted all of the stages that we see here. So we might have a linting stage, making sure that the code itself as code or structure as text, if you will, compliance to some basic requirements that our team or our company wants for readability and so on. Then, of course, we have the testing, unit testing, integration testing. Once all that is good, we can go to the next stage, which is building the application, the service in an actual container. And this container can later on be used in deployments in our cloud native computing approach. In order for us to do this, we publish the newly built container into some registry. This registry can either be some registry that will be used for pulling before deploying these containers into our production stage. We might have one, we might have several production environments, but also it might be just publishing this container for our customers to pull the container and use in their own cloud native solutions. So we had the application, but we want to do container image scanning. We want to make sure that these images are secure. It's actually very easy to do. Here we are showing example with using two open source tools. The first one is called Sift. So Sift is used to generate what is called a software bill of materials, SBOM. The SBOM is actually a big list of everything that's inside our container in terms of libraries and their versions. So for example, those can be the libraries used in our code, whether it's Golang, it's Python, it's Java, whatever we use to create our service. But those can also be packages from distribution. If our container is an actual distribution, those can be deb packages, RPM packages, or whatever we are using. Now, once we have this big list of all the libraries and their versions, we proceed to the next tool called Gripe, again, an open source tool, which takes the SBOM as an input. And then for each entry in the software bill of materials, for particular packages and their versions, it maps to existing vulnerabilities and finally produces a report to see what vulnerabilities exist in that container. So once we have this, that's what we want to have. We want to have the scanning stage. So the scanning stage actually comes right after the container is being produced. Then it's scanned, and if it's good, it's being published. Of course, so far our application was very trivial, and there was nothing that could potentially go wrong, or at least not as bad as otherwise. But of course, we want to add new features to make our service even better. So going back to our trivial example, we introduced some new library that we want to make use of so that we can implement our features. In this case, we are just adding this library, pushing code to the repository, and from then on, the continuous integration kicks in, the pipeline kicks in, we go through the stages, and at this point, we see that something went wrong. So the scanning failed. There was a problem here with the scan, and we'll see the problems in just a moment. But what's important here is that because the scanning failed, because due to the fact that the container does not satisfy the security requirements we have introduced with the scanning stage, this container image cannot be published. So at this point, we say, okay, this container is not yet good enough. It's not secure enough, so we cannot use it. We cannot use it in production. We cannot offer it to customers. So let's see what happened to the container, to the scan rather, and we see a list of vulnerabilities that are now present in our container. At this point, as developers, we realize, okay, we just introduced this library with this version, but it seems that like this is a bit of an old version. It has different vulnerabilities that are known for it. So what we should do is we just burn the library version, ideally to the latest available. We push the code, And we scan again. We go to the pipeline, scan again, pipeline fails again. So there are still things that are not okay with our scanning stage. This is actually a very interesting example because when I was preparing this, I didn't explicitly plan for that to happen, but it did, and it's actually good that it happened because it's a real life example that even if you make sure you're using the latest versions of the libraries of your dependencies, well, maybe they don't use the latest versions of their own dependencies. So you might have some transitive dependencies somewhere that's a bit old or it's vulnerable to something. And eventually you end up with potentially with that problem as well. So what you can do in this example, unfortunately, this does not work always. So sometimes this solution might not work. But in this case, we generate the transitive dependencies, so the entire list of dependencies, the libraries we use and the libraries they use. We find the one that's a bit old, that's vulnerable, that can be updated to a newer version. In an ideal world, if we bump the minor version or the patch version, the patch level, everything is supposed to be good. Unfortunately, sometimes there are breaking changes that are not necessarily intended by the developers. So that's why we have to make sure that if we do this, if we bump these versions, we have to make sure that our product works. That's why, of course, we have testing, unit testing, integration testing. And in our case, everything worked. So first of all, we'll check for that our tests passed and the service is going to work as expected. And also the scanning worked in the sense that there are no vulnerabilities and it passes. We are good to go. This image already complies with our security requirements. Then we're ready to publish it so that later it can be used in actual production environments. At this point, we focused on software composition analysis. Remember the software bills of materials, SBOM. But we can do other types of scanning at the same stage. We can do, for example, malware scanning. Malware scanning means that actually, I'll go backwards. Recently, there has been a case where a company's build infrastructure were compromised in such a way that attackers were able to plant malware in the packages that are being built, whether containers or binaries, doesn't really matter. But malware was injected into their packages, and in turn, their clients were all affected. And what's even more interesting about this case is that this particular company that suffered that was not the first level of the compromise of the attack. It was actually another company which was part of their own supply chain that was compromised, and then the second company, and then all their clients as well. So malware scanning, it's very important, and especially in the context of supply chain. Even if we trust our libraries and our infrastructure, there are still things that can go wrong. Also, image hardening. So we might have some specific requirements, like the security good practices for containers. You shouldn't run, the software inside the container shouldn't be running as root, but also secrets. You might have some leftovers, configuration files, secret files, environment variables, inside the containers, and especially if you provide those containers to your customers to pull and use in their own cloud-native deployments, you should definitely make sure that you don't have secrets as leftovers in your container images. Also, approved base images. That's also an important aspect. So we were talking about going from monolithic application into service-oriented architecture, having multiple services as your solution. But sometimes you operate in an industry, maybe that's financial industry, maybe that's healthcare industry, that has specific compliance requirements. And your development teams, they should be focused on doing services, developing your application, and not everybody to reinvent the wheel how to make the service compliant with this requirement. So it's best to have a set of approved-based images. You have a dedicated team that prepares these images, make sure, of course, that they pass the security scans, but also provide the compliance requirements. And then your development teams can actually focus on doing what they should be doing, developing, right? Creating the services you need. SBOM analytics. This one is a bit of an extra thing you can do. I mean, especially useful from the application security side of things. So that's my role. But since you are scanning the images, you're already generating the SBOMs. Why not store them? Store them as files. Store them in some relational database, non-relational database. Doesn't matter, whichever works best for you. But if you do that, you can actually go and query those SBOMs. Like some brand new vulnerability shows up for a particular library. You can just go ahead, make a query. Do we have this library in which containers? You might not have it, at which point it's great. You might have it in some containers, then you have to go investigate. This is honestly something that has saved us really a lot of time, and has been very, very, very useful from the application security side of things. All right, and for other security controls throughout the continuous lifecycle, you to Tom.
Yeah, so we have scanned our application containers, but we already established that the application code is not the only code that we have. We also have infrastructure as code, so we need to take care of that as well. And again, you're going to be seeing this picture a lot. So you see here at the end of the distribute phase, we have the scan manifest steps, which does this scanning of manifests, where by manifest I mean everything that's not actual code, but more infrastructure as code, like Kubernetes manifests, Docker files, Terraform files, Pulumi files, you name them. And the way it goes is like this. So you have your files, you pass them onto the manifest scanner. This manifest scanner might have some policies configured, depending on what you want to do. And based on the input and based on the policies, it will output a set of warnings, errors, and recommendations for you to fix. So let's go on to a specific example. Let's say that we're running a workload in Kubernetes, and to do that, we need to create Kubernetes deployment object. This deployment object can be configured in multiple ways. And one configuration that we can do is we can decide whether this workload, whether this container runs as privileged or not. And usually it's a really bad practice to run privileged containers, because this means that the container has elevated access to the host, and it's not really isolated from the host machine. So if you're running privileged containers and an attacker manages to get access to that container, they actually get access not only to the container, but also to the host, and from there, possibly to your whole infrastructure. So you shouldn't be running privileged containers unless you have a really good reason to do it, which they are, of course, but that's another topic. So what we want to do is we want to validate that our Kubernetes deployments do not run as privileged. And for that, we can use an open source tool called Open Policy Agent, through which we will pass our Kubernetes YAML files, because Kubernetes resources are declared in YAML files. So we're going to pass it to the Open Policy Agent. We have some policies configured. Open Policy Agent, or OPA, uses Rigu as a domain-specific language for defining policies. You're going to see it on the next slide. And based on that, it will output a JSON document which will show whether we have any violations or not. But first, let's see what Rigu is. So this on the top is a really simple Rigu policy. What it does is it defines a variable called hello, which by default is equal to false. And on the bottom, we have something I like to call a reverse if condition. So if the thing inside the parenthesis is true, so if in the input we have a message property which is equal to world, the thing on top will be evaluated. So hello will be set to true. So on the left, you see the input, which is exactly this, message world. And the output for that in this policy is hello true. On the right, you see that if we change the message to be something else, in the output, we're going to get hello false, because this was never evaluated. And actually, we can use this to write rules that operate onto our Kubernetes resources. So this on the top is another Rigo policy. It's a bit more complex than a Hello World one, but what it basically does is it looks in the spec of the deployment that we have provided. It looks at the security context where all the security information is provided, and it looks whether it's set privilege to true. And if so, it will output violation with this message, which is pretty descriptive, and one can establish what's wrong just by looking at this message. On the bottom, we have our CI workflow where we're actually doing this. And the most important line is the last one. This is where we're using the OPA COI to evaluate the policy. You see the policy.rigo. This is a file again in our repository, which is part of our infrastructure as code. We're evaluating the deploy.yaml file, which is another file in our repository, again, infrastructure as code. And for the input of this evaluation, we're going to look for the violations output for the violations property. And if that is defined, we're going to fail the process so that the CI is read. So a developer commits this deployment, which is obviously insecure. It has privileges set to true, which is exactly what we want to avoid. But once they do this, they will see in their pipeline that the job has failed. So naturally, whatever the developer do when they see a red pipeline, they go to the pipeline logs to see what failed. And here you see on the first line, this is the command that was evaluated. And then after that, you see the result. And you see here, it says container my app is set to run as privileged. This is unsafe. So it's pretty obvious from here what's wrong. So the developer, they know that they would have to go change their deployment to be non-privileged, and they would have to commit again so that the pipeline can pass, they can merge their code afterwards, deploy it, and so on. And this was a simple example of how to do this. And one specific thing for this example is that the policy we used is local, so it's present right next to our code, which is not a bad practice, but it's possible that in this situation, someone abuses this and, for example, a developer that doesn't want to change their deploy to be non-privileged, instead they go and change the policy. Of course, this should be avoided by code review, so this should never pass code review. But if you want to be even more secure and not even allow that, we can use for example, some product that doesn't define local policies, that uses, for example, stores policy in the cloud. And by having good access control, the developers won't even have access to these policies, so they will never be able to change them and work around them. One such product is Carbon Black Cloud, which is what I'm showing here. I'm creating my own policy. Here I'm choosing from the available rules. So here we have the rules actually predefined for us. So we have a set of rules we can choose from. And actually I chose to enforce two rules for my resources. The first one is called allow privileged containers, which does exactly the same thing that you saw with the Rigo policy. But the second one is called enforce not root. And this enforces that the user specifies a user for the container to run with. And that user should not be root, which is another good practice to enforce. And on the left, we see that we have other available policies we can choose from. So again, I'm creating my policy. I will confirm the policy here. And now I can actually write another CI job which uses not OPA, but uses the Carbon Black COI to enforce this rule. And again, we see the last line of the job, which is the most important one. We use the COI to validate the Kubernetes object, and that will fail if you have any violations. So again, a developer again commits a deployment that violates this policy. This time they set the run as user as 0. 0 is the root user. We want to avoid this. So again, the CI will be failing. They check the output of the CI. Again, we have descriptive error saying what exactly we are violating, which file this is, what's the risk. So the developer can just go and fix the violation. And once they do this, we see here privileged false, run as user 1000, which is a non-root user, and now the CI is green, and they can proceed to merging and deploying their code. So these are two ways to enforce, to do manifest scanning and enforce on that. Open policy agent, where you have local policies, you have to write them from scratch in Rigo, and you don't have a set of predefined rules to choose from. Or something like VMware Carbon Black, where policies are in the cloud. You can choose from predefined rules, and you can also write your own. And of course, there are other alternatives as well, Kyverno, kubesec, kubespace, kubescape. These are all open source products that work in a similar way. You can define policies, you can choose from predefined rules, and you have some sort of a COI to use in your CI to validate these policies. And the good thing with products like this is that you don't actually have to be a security expert to use them. Instead, they give you recommendations and they give you predefined rules which you can choose to enforce in your environment. Of course, knowing some security is good. Okay, that was about manifest scanning. If you have any questions, put them in the chat and we will answer them later. But right now we're going to talk about another step of the distribute phase, and that is artifact signing. Signing is, well, signing your artifacts like container images, binaries, packages, whatever, everything that is produced from your code in a way that you can verify the signature later to make sure that the artifact that you're using is trusted and has been produced in a trustful manner and has not been tampered with. The workflow looks like this. So we do this in the CI pipeline after we build the artifact. We have some set of keys which we use to do this. And later, when we want to use the artifacts on the right, we pull the image, for example, and we verify the signature. I'm going to give an example for artifact signing where I'm going to sign a container image, but you could use this for all sorts of artifacts, like binaries, packages, etc. The reason we want to do this is, for example, on the top we have a trusted actor, a developer, our CI, that is building a container image and signing it and pushing it to the container repository alongside its signature. And later, when Kubernetes pulls the image, it can verify the signature. While on the bottom, we have a malicious actor that built a malicious image and managed to find a way to push it into our container repository. But because this actor never has access to the key, they cannot sign it. So this image will not have a signature, or it will have a signature but not a valid one. So later, if they manage to find a way to trick Kubernetes to run their malicious containers, Kubernetes will never allow this because it will validate the signature and it won't be valid. So this is a good reason to be signing your artifacts. And again, we're going to do a specific example. We're going to sign a container image, and later when we deploy that image, we're going to verify the signature before deploying. For that, we're going to use an open source tool called Cosign. And again, we're going to do this in our CI, which is where we build our images. Again, it's just a single line of code, the last one. We use the Cosign COI to sign the container image that we have just built. And the important thing here is that we're giving it a key. This is the private key that we use to sign this image. And this is the most important thing in this workflow. Your key should be secure, should be stored securely, because if someone stole your key, it's game over. They will be able to sign everything, and that will be later verified that it's legit because they have your key. So make sure your keys are safe. And you see, before that, we are actually doing a Docker login. We need this because when Cosign signs the image, it actually pushes the signature to container registry. So this way, Kubernetes later, when it pulls the image, it can also pull the signature and verify that. Or if it doesn't find the signature, it will fail. So this is how the CI output looks like. We have on the top the command, which is the same that you saw in the previous slide. And on the bottom, we see that we have successfully pushed the signature to container registry. In the middle, you actually see that there is a warning output by the Cosign tool. This warning is telling us that we are signing a tag. The tag is called Cosign. This is the last part of the container image. And Cosign is telling us that we should not be using a tag, but a digest, because digests are immutable, but tags are not. So what's behind this tag now can change, and tomorrow it can be a different thing. So we can never be sure, even if it's signed, we can never be sure it's the same thing. While manifests, they are immutable. So if we sign a manifest, at this point, we are 100% sure that no one has tampered with it because it's cryptographically signed and it's immutable, so no one could have changed it. So the best practice is to sign tags and to use tags later when you deploy them. Not tags, manifests. And here, this is a screenshot from the container repository. And you see on the top, we have 4 images. And on the bottom, we have 4 SHA digests. And these are actually the digests of the signatures. So these are the signatures that Cosign push to our container registry alongside our images. Okay, this was only the first part of the exercise. So we have signed the container images, but we are not yet verifying them. And the question here is, where should we verify the signatures? We could do it again in the CI, but this doesn't make much sense because we are already building these images in the CI. So we kind of know that the CI is something we trust. Instead, we need to strive to do this verification close to the deploy phase. So ideally, as closer to the runtime phase as possible. That is so, you can see it here. So we have the sign step part of distribute phase next to the container image build and push, but we have the verify step all the way in the deploy phase because we want to do this at the orchestrator level, not in the CI, because if we do it in the CI, someone might work around the CI and try to deploy an image in a different way. But if we do it in Kubernetes or whatever platform we use, then the platform will enforce that, and whatever way you try to deploy something there, it will be verified. So let's see how we can do that. Luckily, Kubernetes gives us a really easy way to do it. It has something called validating webhooks, and this is a pluggable mechanism for deploying additional verification logic for your resources. So you can deploy a webhook, you can register it with Kubernetes, and Kubernetes will call it each time that you try to create some sort of resource, in our case, a deployment. And if that webhook denies a request, Kubernetes will respect the decision, and it will also deny the creation of this object. So the object will never be created. And anyone can write their own validating webhook in their favorite programming language. The architecture of Vue looks something like this. On the top, we have the Kubernetes API server. And on the bottom, we have a user that's trying to create a deployment. This could be a user that's running this command on their machine, or it could be our CI, it doesn't matter. They're trying to create this deployment, they're doing kubectl apply. This goes to the kube API server. It passes authentication and authorization check that the user can do this operation, create deployment. If that's allowed, it goes to the validating webhooks. And if any one webhook denies a request, Kubernetes will also deny the request, and the user will get an error saying why their request is denied. If all webhooks allow it, it will pass to the next stage and eventually will be created in Kubernetes database. So we can write a validating webhook that validates our image signatures, but actually we don't have to do it because Cosign already did this. They have implemented a webhook which does this, and you can just deploy it and configure it and use it. The installation is pretty simple. Here I'm using Helm to install the Helm chart, which again they are providing for us. And after we have installed it, we need to configure it. The configuration is this resource, which is called custom image policy. And there are 2 interesting things here. The first thing is on line 7. This is telling us which images we want to validate. And the 2 stars means that we want to validate every container image. So absolutely every image will be validated by this policy. And the next thing on line 8 through 15 is the way we want to validate it, which are our authorities. And this we have provided our public key, which we have used for the signing. So for the signing of the image in the first phase, we have used the public-private key pair. This is the public key. This is safe because it's public, so it's safe to be here. It's safe for me to show it to you because it cannot do anything else apart from validate that the image has been signed with the private key. The private key you must keep safe. The public key is safe to show around. So what this will do is you tell the Cosign validating webhook to validate that all the images that are being deployed into our cluster are signed with this public key. And here I'm trying to create a deployment. For this, I'm using this image, which I have tagged non-signed, and I have not signed it. And when I apply this to the Kubernetes cluster, I get a bad request error, and I see that the error is because there is no authority for this image. There are no matching signatures. So the image is not signed. Kubernetes doesn't allow us to deploy. If I try to deploy another image which is signed, this gets created successfully, and I see that my deployment is already created in Kubernetes and it's ready to be provisioned. you don't have to trust me on this. You can actually go to my container registry on GitHub and see that there is a signature for the signed image, but there isn't a signature for the non-signed image. So you can actually verify this yourself. And again, we are signing the image in the build phase, in the distribute phase, in the deploy phase, in the orchestrator. We are verifying that this signature is intact and no one has tampered with our image. Runtime.
All right, runtime phase. Again, this picture here. So so far we've been building containers, testing, scanning the container images, the manifests, also signing them, make sure we have policies for all these. And finally, our services can actually run and do what they're supposed to do and be useful for us and for our customers. So the rightmost phase, the runtime phase, we will have different continuous checks, monitorings, also policy enforcements as mentioned. So let's dive into this a bit. The first thing that we're going to talk about here is service mesh. Now, service mesh is its own very important, big, and very interesting topic. It's definitely worth a dedicated session or maybe even more than one session. But on the high level, the service mesh is actually a dedicated infrastructure layer. So instead of our developers focusing on how our services will communicate to each other, how they authenticate between each other, the services themselves, we can do that in the service mesh in this dedicated layer so that developers can focus on the actual service, the actual logic that we want to implement and to run. So service mesh takes care of things like service-to-service communication, what container or what service is allowed to talk to what other service, how do we tell them apart, how do we authenticate them, how do we authorize them. The communication itself, we can secure through service mesh. We can use TLS, we can even use mutual TLS for that. Also, in our cluster, what kind of services do we even have? This is something else that the service mesh can help with. Traffic control, routing requests, routing packets between these services. So retries, failover, rate limits, quotas, and so on. And also observability, how much traffic is going through each service, and what talks to what. We have logs, we have traces of all that activity. And so far we've been looking at code, configuration files, YAMLs, JSONs. But since we are in the runtime phase now, we can actually finally see how all this works, right? And we can see it in terms of statistics, but we also can see it in a more visual way. This is here an example of interaction between different services in our application. We can see that there has been traffic parts of the application. So some services are much more heavily used than others, which is of course very, very important for us to help us fine tune, for example, maybe have more containers running for these services to handle the load, or maybe the service itself is somehow not as optimal as we want to be. And by looking at, because of the observability we get from the service mesh and from the runtime and all the metrics, we can pinpoint different problematic areas. Also at the bottom, we can see the load for the application, for the whole cluster. It's definitely something very, very, very useful. But service mesh is its own topic, and it's worth having a dedicated discussion for that alone. That's the high-level overview of the service mesh. Next thing I want to mention is secrets management. Now, since we went from a monolithic application to services, secret management becomes a bit more involved. Now, we have different services that will have different requirements for credentials. Some will have the need to talk to a database or database credentials. Others might need to talk to just other services. And there will also be some that will talk to external providers, cloud providers, or other external services. So that's something that's definitely not exactly trivial to solve. So first, you have to decide how do you want to manage your secrets. do you want to manage them natively in your orchestrator? And even if you do that, you still have to figure out, do you want to encrypt the secrets or do you want them to be plain text? And if you decide to encrypt them, so you have to encrypt, decrypt, meaning that you need to handle some keys for that. Who handles the keys? Is it the orchestrator or is it some external key management service? Whether this is on-premise solution or if it's cloud solution, it's also an option that you have to figure out how to fit all the blocks in there. Or you can do something else. You can actually use an external secrets manager. So that is a product or a service that manages all the secrets. Of course, it works through integration with your orchestrator so that these secrets can be injected into the services, into the containers, so that at the point at which the service needs the database credential, it is available to the service and it can read it and it can use it. The secret manager can also rotate the credentials. So instead of having some static keys somewhere stored in whatever location that are hard to manage, that someone has to manually go and rotate, you can actually use the secrets manager to do this for you. What's actually even more interesting is that with the secrets manager, you can have ad hoc or dynamic credentials. So again, imagine you have a service talking to some cloud provider. Now, instead of this service always having the cloud provider credentials or the keys for that, how about the secret manager provides a dedicated credential to this service that's only valid for, let's say, 1 hour or 6 hours, 24 hours, how much ever time you need. In this way, even if something bad happens and the credential gets compromised, first it can be scoped so that it's very limited impact in terms of what can be done, and then it can be scoped in terms of time, so how much time this credential will be valid. Definitely great option, but also not entirely trivial to do, and there are things we should consider, and this is also worth a dedicated discussion on its own. With other things in the runtime, I had to Tom.
Yeah, so next thing on our agenda is container behavior. Again, I guess you wouldn't be surprised if we tell you that this again is a pretty complex topic that deserves its own lecture or set of lectures, but in a single slide, we have containers, they are doing something, they're doing some job to be there, there's some work to be there. They're executing network connections, they're making syscalls to request native resources. And it's good to have a sort of security agent that will monitor this behavior, the connection, the syscalls. And when you have that, you can actually send this data to an analytics platform where the data is analyzed and maybe have some sort of anomaly detection. So, like for example, this container did only this for 1 week and then it started doing something completely different. Probably an attacker got in and trying to do something funky. Basically, observability, having this sort of information on your containers, it's always nice to have and pretty important to have nowadays. Resource limits. So we are running containers. These containers, we have multiple containers running on the same node, so they're actually sharing the resource of the node. And each container, it requests some sort of resources, CPU, memory, and they can request more if they need. But it's good to always impose some set of limits on those, because let's say we have an error in our application and it has a memory leak. So the container will continue requesting more and more memory until there's no more memory left on the node, and the other containers there will be no memory left for them. So the other containers will die as well, or the whole node will go down, and alongside it, the other containers. Or even worst case, an attacker manages to get into your container and they started mining crypto. So they're going to be using and requesting a lot of CPU power. And if you don't have any limits for that, probably your node will go down, and alongside it, the other workloads which are healthy. So yes, and yes, having resource limits is good, but if you want to enforce that your containers have resource limits, in Kubernetes it's just one field where you specify the limits, and you can actually go back to the admission control, to the manifest scanning, and you can actually enforce there that all your deployments have defined request limits for memory and CPU. So this here is in runtime, but you can actually enforce it way back in the distribute phase, so that you have a secure runtime.
All right. So as a summary, we've touched different security challenges in the cloud native computing approach. But what's actually important is, on one hand, yes, there are challenges. Some things are more complicated than before. But also, if you manage to do this well enough, your application and your overall security posture will be actually much better than before. And also, it's very important that there are things that you can easily do, you can easily implement that will give a great boost to your security posture. Like, for example, what we were focusing a bit more on, the container image scanning, the manifest scanning. You can literally have this by the end of the week or next week, and you can already see some results. Of course, there are a lot of nuances. There are other complicated things as well, but it can get much better.
Absolutely. Thank you all for the attention, and we're ready to take some questions.
Thank you for the great presentation. Now it's the time for questions. You can paste it in the chat, I can read them, or you can unmute yourself directly. Yeah, don't be shy. It's good to have a discussion. And the topic is quite, I would not say even interesting. It's just the way that things need to be done.
Absolutely, it's the way things are now.
Okay, maybe I can start with a question I saw on the slide. Something evolving around eBPF. Can you explain a little bit more what the eBPF means and how it helps with connectivity and security?
Yeah, of course. So eBPF it's a technology that allows you to write mini programs which run in the kernel. So when we are writing applications that we deploy them somewhere, they run in user space. But with eBPF, these programs that we write with eBPF, they run in the kernel space. And this gives us great visibility inside what's going on in the kernel. And that's why it's here. That's why it's really useful for things like observability and networking and security, because it has access on a really low level. So it sees a lot of things that you might not see in user space. And it sees them early. So even if you want to do some sort of prevention, you can actually do it with eBPF, for example, to block some network requests based on their origin. Yeah, this is in 2 sentences what eBPF is. Great question.
Thank you. So, any other questions from our viewers? Okay. So, in that case, let me thank from the whole group again, Martin and Anton, and we would welcome you on our next session from the Meetup SaaS series. Thank you all, and bye for now.
Thank you. Bye.
Thank you, everyone.